Hello YouTube, this is Brian, and today we are going to talk about Cauchy's integral formula. From our last video, we learned that if you took the contour integral and chose a path that walked counterclockwise around the origin, around a simple monomial, as you can see right here, x to the n, just a simple monomial where n is any integer except -1 for the first example here, you will get 0. For that special case where n is equal to -1, it simply just turns into the fraction 1 over x. And when you integrate around that, around a counterclockwise direction, as you can see here by the contour graph, you will get an answer of 2 pi I. We figured all this out in the last video, and today we're going to see how this is really powerful for us, and we're going to exploit this power and somewhat heuristically derive Cauchy's integral formula. So let's go. The way we're gonna do this is we're gonna do a little quiz, and I recommend for anyone out there that thinks I'm going a little too fast, go ahead and pause the video and work out the problem yourself. Go ahead and substitute x is equal to e to the I theta, and dx is equal to I times e to the I theta d theta for each problem, and you'll see that you'll get the same answers as me. And you can always go back to my second video on contour integrals to see how this is done. So let's go. This video I'll try to go fast in this video. This will be a fast video. So let's just do it. Let's just go. So the first problem here is the integral around the just the function x. Well, since it's not 1 over x, we just know that this will just be 0. And let's see if I'm right here. Yes, I'm right. Okay. So let's go ahead and give myself a little happy face there. So that was easy. Oh, and now we got to the integral around 1 over x dx. And this is obviously the only special case where it's not 0. And this is equal to 2 pi I. See if I'm right. Okay. Hey, I'm right. Okay, we're doing good. We're doing good. So let's go to question number 3 here. Looks like our function now is 1 over x cubed. Since this is not 1 over x, if we do the substitution e to the I theta, we will get 0 because it'll just work out to be 0. Go ahead and do the substitution on paper if you'd like, or refer to my last video if you get confused. Let's see if I'm right. Yep, I'm right. Okay, yes, we're doing good. Great. Okay, let's do the next one here. Oh, we're getting a little bit more complicated. So we're going to just focus on this integral right here. We'll ignore the 1 over pi I, 2 pi I over here. We'll save that for the last. We'll save this for last. So what is this? It's just an infinite series. It's going to look like this. 1 over x, 1 times x to the first power, plus 2 times x to the second power, plus 3 times x to the third power, and so on. And these are all over x to the 70. So you can see right here. And this will keep continuing on. 68 to the 68th power over x to the 70 plus 69 over times x to the 69 power over x to the 70. And that will just keep going on and on and on. The reason why I wrote these two terms out because every single term in this infinite series, when you do the division, when you do the cancellation of, these x's, when you integrate around the origin, these will all turn into zeros because it's not in the form of 1 over x. Even the 68 term will go to 0. And the only term in this whole series that will pop out any number other than 0 is this term. Because what does this reduce to? Well, it reduces to 69 over x. Okay? And if you do that integral, put a little dx right there, let's see. This is going to equal 69 times 2 pi I. Well, look over here. See this 1 over 2 pi I? That's interesting, right? So we do a 2 pi I. Sorry if I'm going in a weird circle here. You'll see that these 2 pi i's cancel, and we're just left with the number 69. So we're looking good. Sorry for my little cell phone popped up there. Yeah. Okay. Oops. Yeah, we're doing good. Sorry, I'm on my note 8 here. And let's see if I'm right. 69. There, am I right? Hey, I'm good. Okay, let's go to number 5. Okay, this is just probably a simpler version of what we just did. I'm just gonna guess it's 19. But wait, the path is going backwards. So if you do the whole substitution of e to the I theta, and now that you're going backwards, the integral, its angles that it goes through will start at 0 and then go to negative 2 pi I. So you're going clockwise this time. And when you work it all out, you'll find that the answer isn't 19. It is actually equal to negative 19. Let's see if I'm right. Yes. Okay. We're doing good. We're doing good. Okay. Number 6. Oh, we got something else here. We got a 1 over x minus a. 1 over, so x minus a. And looks like our contour shifted to go around the a, as you can see here. I'm going to assume that, there's nothing special about the origin and that the whole space acts mathematically the same to any other parts of the space. So I'm going to assume that this is 1, because we got to, this integral just equals 2 pi I, but once you divide by 2 pi I, then it equals 1. And if you were to go ahead and do the substitution for x is equal to 2, if you're to do x is equal to a plus ei theta, and dx is equal to I theta, you'll see that, in fact, space does act the same no matter how you shift the graph. Remember from high school algebra that you can shift any graph by subtracting the constant that you're shifting by. So let's see if I'm right here. Yep, I'm right. Okay, number 7. We are. This is a big one. So looks like we have another shifted graph, and let's just focus on this integral again. And n could be any natural number, as we can see down here. Any natural number. So what's the answer? Well, on most of natural numbers, it will be 0 because you're not left with the fraction 1 over x minus a. We only get something if we have it in this form. So we want n to be 1 more than 4, because we want a 5 down here, right? We want a 5. So n is equal to 5. And if that is true, then the integral will equal 2 pi I. And then once we factor in this part of the equation, we divide by 2 pi I, which is 1. And then we times by n plus 1, as you can see on the top there. Well, we know that n is 5, so we're going to say that this is 6 when n is equal to 5. So let's see if I'm right here. Equals 6 when n is equal to 5. 0 for all other n in the natural numbers. Great, we're doing good. Okay. And now we're at the final problem of our little math quiz, and probably the main point of this discussion. So now we're doing this integral of a generic function, f of x. Interesting. See, what does f of x look like? What is that? We can't really do any cancellations. But then we're giving a little hint down here. This is a big hint, actually, and this is this is actually a big deal. We know that n is in the natural numbers, and f has a Taylor series in the region C. Interesting. That is a big deal. So if it is true that f of x has a Taylor series in region C, this region right here, we know that we can write f of x to be the infinite series. We're going to use k as our index here. K is equal to 0. And f of, this is a derivative indicator here, superscript, f to the kth derivative at a times x minus a to the k power over k factorial. This is the Taylor series. That's my little Poochie over there. Hey Poochie, you're so cute. This is the Taylor series, and as you can see, if we let k equal to n, you'll have an n up here and an n plus 1 on the bottom, and that will be the term that pops out a number other than 0. So we're going to use that to our advantage, and that integral, all the sums, all the terms will be 0 except one term, and that term will just leave behind an f to the n at a over n factorial, and then of course we want to evaluate the integral. It'll always pop out of 2 pi I. And then as we look up here, I'm going to circle this term that's out in front. Look at, when we times that in, these will cancel, this will cancel, and all we're left with is an f to the nth derivative of f evaluated at a. And let's see if I'm right. Oh, yep, it looks like I'm right. F to the nth derivative evaluated at a is equal to this. And this, my friends, is the Cauchy integral formula. It is the generalized version. And this is one of the most powerful formulas that we have come across so far. This is a big result. Big result. Okay? Big deal. And these videos, these first couple videos are meant to be a kind of a refresher for people who've taken complex analysis in the past, or just a tutorial trying to get people caught up to using contour integrals, because as you might know, this channel is going into fractional calculus, fractional complex calculus. And what that means is that we're going to take this generalized Cauchy's integral formula, and instead of using natural numbers, we're going to allow the domain of discourse to be any complex number. You know, think about taking a complex transcendental derivative of a function. Okay? Like imagine taking a pi ith derivative of a function. What happens? Well, we're going to find out. And it's going to be the most amazing stuff you'll ever see. I promise you. I believe my next video will be doing the functional equation. As you can see by this slide right here, we're going to use this assumption that we can take complex non-integer derivatives of functions, and we can get some very, very powerful results. This will be my next video. And it will be a long one. It'll be one of the most unique derivations of the functional equation for the zeta function that you might see on the internet. So that's it for today. Go ahead and if you are feeling generous, give me some pizza money at my Patreon or PayPal. There's also a Bitcoin in the description box if you want to, send some crypto to me too. And yeah, that's it. Thank you and have a good day.